Hello everyone, this is Amruta from Department of Electronics and Communication Engineering, and my tech talk topic for essentials of problem solving is the traveling salesman problem, a survey of modern techniques. Coming to the introduction, the traveling salesman problem TSP is a classical optimization problem in which a salesman must visit a set of cities exactly once and return to the starting city, minimizing the total distance traveled. So the salesman must visit every city exactly once and return to the starting city by reducing the distance traveled, total distance traveled. And TSP has numerous real world applications in logistics, transportation, and network design. Modern techniques aim to find efficient solutions to large scale instances of TSP. So this TSPs which has many real world applications, and modern techniques aim is nothing but to find the efficient solutions. And in the right side you can see the traveling salesman problem. What's the shortest route to visit all locations and return? This question by the salesman. So the adding more stops takes longer and longer and longer to figure it out. So by taking more takes more stops, so that it will take longer time, so that we will reduce the total distance, and by minimizing the each distance, means minimizing the average distance of the total path, and we will find the final minimum distance of the problem. And coming to definition, the traveling salesman problem can be formally defined as follows: given a list of cities and the distances between each pair of cities. So list of cities are the, here you can see the list of cities are represented as dots, and the distances between cities are represented as the arrows, blue and orange. So mathematically, objective, find the shortest possible route that visits each city exactly once and returns to the original city. This is the main objective of the TSP. And mathematically, the TSP can be represented as finding the minimum Hamiltonian cycle in a weighted graph, where the vertices represent the cities and the edges represent the distances or costs between them. So this edges will represent the distances or cost between the cities, and the vertices will be represented as the cities. Coming to the brute force approach. The brute force approach involves evaluating all possible permutations of city sequences and selecting the one with the minimum total distance. So by evaluating this all the permutations of every city, so we will find the minimum total distance of the problem. And this approach is impractical for large problem instances due to its exponential time complexity. So this approach is important for the, it's crucial for the large problem instances, so that it reduces the complexity. And brute force remains a benchmark for evaluating the effectiveness of modern TSP algorithms. So that this brute force will remains the perfect benchmark for solving this effectiveness of modern TSP algorithms. So here right side you can see the analysis of brute force method. P of x equal to an into x so on into x plus, and here right side n multiplications for n minus 1 multiplications, and for n minus 2, so on, 2 multiplications, 1 multiplication, and n is the total additions. Coming to the exact algorithms for TSP. Exact algorithms such as branch and bound and dynamic programming aim to find optimal solution to the TSP by exploring all possible permutations of city visits. So by exploring all the permutations of this every city, by visiting every city, we will able to find the optimal solution of this traveling salesman problem. These algorithms guarantee the optimal solution but can be computationally expensive for large problem instances. So these algorithms give the guarantee solution, but it can be expensive for the large problems. And exact algorithms are suitable for small to medium sized TSP instances where optimally is crucial. So here optimal solution, finding the optimal solution is crucial in this exact algorithms for TSP, where the branch and bound and dynamic programming. Coming to the approach, branch and bound. The branch and bound approach for the traveling salesman problem explores potential routes, calculates lower bounds to estimate the minimal cost, and prunes paths exceeding the best known solution, aim to efficiently find the shortest possible route that visits each city exactly once and return to the starting points. So in this approach, the salesman explores by calculating the minimum cost and getting the better solution by finding the minimum shortest possible route, and the starting and ending point means every ending city is same. Here you can see in this diagram where it's a tree diagram. Here you can see cost, first one cost equal to 25, and here where the red color mark means red color line, you can see the minimum cost, minimum edge for the required city, and this cost is 25. And coming to the third one, the cost is 28, and fourth 28, and fifth also 28. So by this approach we can find the minimum shortest possible route for taken to the problem. And approximation algorithms for TSP. Approximation algorithms provide near optimal solutions to TSP in a more efficient manner compared to exact algorithms. So compared to this exact algorithms, this approximation, so in the name only we can say we will get the approximate solutions for the in TSP, where in more efficient manner we will get the optimal solutions. And popular approximation algorithms for TSP include nearest neighbor, Christophid's algorithm, and Lynn-Kernighan heuristic. While approximation algorithms may not guarantee the optimal solution, they are practical for large scale TSP instances. So these are not guarantee. These approximation algorithms were not guarantee for this optimal solution, but they are practical for the large scale traveling salesman problem instances. Next, nearest neighboring algorithm. The nearest neighboring algorithm starts from a random city and selects the closest unvisited city as the next destination. So for example, here we can see in the left side, here question mark is a city. So let's assume that question mark is a city here, and these are the neighboring cities. So here if we will pick the random city which having the, so question mark is the random city, so we will select the closest unvisited city. So it should have which is not visited, and it should be near to the random city. And while efficient in terms of time complexity, nearest neighbor may not always find the optimal solution. So where it is efficient in time complexity, and but this nearest neighbor may not always find, so there is no guarantee to find every time the optimal solution. Variants of nearest neighbor such as the farthest insertion heuristic aim to improve the quality of solution. So the aim of this farthest insertion heuristic is to improve the quality of solutions. Coming to the meta-heuristic techniques for TSP, Meta-heuristic techniques such as Meta-heuristic techniques such as genetic algorithms, ant colony optimization, and simulated annealing are widely used for solving TSP due to their ability to efficiently explore the solution space. And these techniques offer a good balance between solution quality and computational efficiency for medium to large TSP instances. So these meta-heuristic techniques, which provides a perfect balance between the quality and efficiency for the medium to larger TSP instances. Meta-heuristic algorithms can be fine-tuned with parameters and heuristics to improve performance on the specific TSP instances. So here you can see the genetic algorithm. It's like type of a flowchart, and here we can see the start option and second set GA parameters and generate initial random population and so on. There is here yes or no for the optimization. If it is okay, if it is optimized, they are best chromosome. If they are not, here we can see the parent selection for next generation or crossover of parents chromosome and mutation of chromosome. And here you can see ant colony optimization ABCD. So ants go from food to nest in A. In B we can see from ants travel from, there is an obstacle where traveling from nest to food in B. So in C we can see there is an obstacle but they can cross above this one, and in D option you can see there is an obstacle below the root of the food and nest. Here we can see the simulated annealing. X-axis represent the iteration and Y-axis represent the fitness. Coming to the applications of TSP in real-world scenarios, TSP has practical applications in various industries including logistics, transportation, supply chain management, and route optimization. Companies use TSP algorithms to optimize delivery routes, minimize travel costs, and improve operational efficiency. So TSP algorithms play a crucial role in solving these complex routing problems and optimizing resource utilization in real world scenarios. Coming to the conclusion, the TSP remains a critical benchmark in optimization with modern techniques significantly enhancing the solution capabilities. So this TSP remains a benchmark for the optimization. And while exact algorithms provide optimal solution, these exact algorithms will provide the optimal solution, and these heuristics and meta heuristics offer practical approaches for the larger instances. Future advancements may arise from hybrid methods and emerging computational paradigms continuing to push the boundaries of TSP research and applications. By combining the diverse optimization strategies and leveraging the power of computational technologies, researchers are making strides towards more efficient and effective solutions for TSP in the digital age. So, by combination of these diverse optimization strategies and the leveraging the power of computational technologies, so these researchers are making the more effect towards the effective efficient solutions of the TSP in the digital age. Thank you.